All right, so we're in the chapter on exergy. We were talking last time about water in a rigid tank that's electrically heated. Remember that problem? We were working through it. We did see the pattern, talk about energy, talk about entropy, lastly talk about exergy. You recall? I know it's been a couple days since we've talked about this problem. And so the change in energy, exploit the property, that it's a property. Energy, internal energy is a property. So the change in U is M times U2 minus U1. Fix the state and get the change in U, and you have the change in the property. To get the energy transferred by the electric work into that rigid tank, we used first law. And then we solve for the energy transfer. Let me use a W on that. W electric. Okay? And then that turns out to be equal to the change in U because it was insulated. We did that last time. Okay? But see the pattern? Exploit property, exploit first law. Second, entropy, change in entropy. Guess what? Entropy is a property. Property. Fix the states and evaluate the property entropy. So the change in the entropy is M times S2 minus S1. The amount of entropy transfer with the electric work. We talked about that last time. What was the answer? 0. And it's an idea that entropy can be transferred with energy, but only with heat transfer, not with work transfer. Entropy is a measure of disorder on a molecular level. All right. So this was 0. How about the amount of entropy production during the process? Sigma. How did we solve for that? Entropy balance. Second law. Entropy balance. And then we found the entropy, the amount produced is equal to, actually equal to the increase. True? See the pattern? Exploit the property, exploit some balance equation. Exergy. Change in the exergy of the water. That would be delta E is equal to M times E2 minus E1. How would you solve for part A? It's a property. Exergy is a property. Internal energy is a property. Entropy is a property. You already have the states fixed. Just evaluate the property. How about the amount of exergy transfer with the electric work? Part B. Is any exergy transferred with work? With work transfer. We had an equation, let's say like this. Any entropy, exergy, I keep saying. You get tongue twisted in this business, right? Is any exergy transferred with heat? Yes. So if I had this much heat transfer, I'd multiply by 1 minus T dead state over the boundary temperature which the heat was transferred. And that would be the amount of exergy transferred with the heat. True? Can this ratio be greater than 1? This fraction. No, it's less than 1. It's a percentage. It's a Carnot efficiency. Okay, let's do this. Any exergy transfer with the work? It's just the work. With what multiplying? 1. It's a 1-to-1. If I have 1 kilojoule of work transferred, I have 1 kilojoule of exergy transfer. The only time that that's not true is if I have to subtract off the non-useful component of boundary work, pushing back the boundary, the atmosphere. That's the only other time. That's the only time. But this I have electric work. It's 100%. So guess what the answer for part B is? The exergy transfer with the electric work is equal to the electric work. If your sign convention is the work in is positive, that exergy transfer in will be positive as well. Sign convention is the work out is positive, then it will be a negative electric work, and then you have to say that that exergy transfer is a negative quantity in. How does that make sense? Or a negative out, sorry, a negative out, which would be a positive in. How about the last part, C, amount of exergy destroyed during the process? I would say exergy balance. And so what does our exergy balance equation look like? It looks like the final exergy minus the initial exergy. So the change in exergy can go up if I have an exergy transfer with the heat coming in, can go up with the exergy transfer with the electric work in, can go down if I had, whoops, let me erase some of this, can go down if I have a work out, and it will go down if I have any destruction. You say, didn't you write this equation twice, kind of work, work? Yeah, but I emphasize I can talk about work in and I can talk about work out. Work in is going to add a positive contribution, work out will add a negative contribution. So in this case, I prefer to talk about the positive electric work in, no work out. The tank was insulated. So what we find is that the exergy destruction is equal to the change in the exergy, is equal to, let me see if I can get the signs right here, negative the change in the exergy plus the exergy transfer with the electric work in. Make sense? All right, I recorded this and put it up onto the internet, or I'll have it up by end of today. Okay? We have an exergy balance equation for a control volume. Here is in general, this is steady state. I have exergy flowing in with some heat transfers. I have multiple heat transfers, so put a sum on it. Inside the bracket, it looks like the Carnot efficiency. What is this TJ right here? That's the boundary temperature at which that particular heat transfer is coming into the system. All right. What's this T naught right here? Dead state temperature, 298 Kelvin typically. What is this W minus W dot CV? That's some typically a rotating shaft power coming out of the control volume, so it's a negative. Okay. For the previous problem, we added in here a positive W dot electric going into the system. You can modify these equations, right? You can adapt it. If you get a different thermodynamics textbook and you look at, you say, well, this author wrote it slightly different, right? All right, then we have, for each mass stream coming in, you bring in flow exergy. And for each mass stream going out or exiting, it takes its flow exergy, just like enthalpy in the previous energy balance. Here's the equation for flow exergy, H minus H naught minus T, S minus S naught, kinetic and potential energy. Okay? And then you still have the potential to destroy exergy. What's exergy again? The capacity to do useful work. Raise a weight in a gravitational field, mechanical work. This is derived and put online plus in the textbook. But what I thought I would do is I'd give you a brief derivation for this flow exergy term. So here's a brief derivation for the flow exergy term if you're ready for it. Think about a control volume that has one inlet, and an inlet, it's coming in at temperature or pressure P, temperature T, kinetic energy, potential energy. It's all coming in at some enthalpy, some flow rate, etc. It has one outlet, and it's going out at P naught, T naught, kinetic energy approximately the same as the potential energy is 0. Now, if it comes out with an absolute kinetic energy absolutely positively equal to 0, how is it coming out if it has no speed? It's got to dribble out somehow. So just say it's negligible kinetic energy. All right, otherwise it has no velocity. It's not going to cross the boundary of anything. But it comes out at the dead state. All right, so you have one shaft for work, and you're going to do an exergy balance. So here's our system. Here's our in over here. Here's our out, exit, and it's at the dead state. And we're really interested in putting as much of the energy that's coming in with this stream of flowing fluid. It's coming in with m dot and leaving with n dot because it's steady state. So it's what flows in, flows out, and you want to convert or produce as much shaft power coming out of this control valve. You want to maximize this right here. Okay, that's the goal. Well, could we also have some heat transfer into the system? Yes, you could. Let's leave it in the traditional sign convention, Q dot in. But because we don't want that Q dot to be adding or removing any exergy, we're going to do an exergy balance. What we'll say is you could have some heat transfer, but let's say it happens at the boundary temperature of the dead state such that the exergy in or out with that Q dot is 0. Make sense? Now let's do an energy balance. Energy balance for this system. We have steady state, so no accumulation or depletion of energy in the control volume with time. We'll have the Q dot into the control volume, because that Q dot doesn't have to be 0, it's just not carrying with it any exergy because I made the boundary temperature T naught, the dead state temperature, minus W dot CV, and that's what we want to maximize. We want to maximize the shaft power out, the useful mechanical power out. We're coming in with some enthalpy and some kinetic energy and some potential energy, and we're going out with some enthalpy, but that's a dead state enthalpy. The dead state kinetic energy, hey, that's 0, and the dead state potential energy, that's 0. So it's just clean up a little bit. It's just that's the mass flow rate times the enthalpy, kinetic energy in, potential energy in, minus the enthalpy out at the dead state. Does that contribution look good for the energy balance? Thumbs up if you follow. Ask me a question otherwise. Look good? Okay. Was there any other term in the energy balance equation that I left off about exergy? Exergy balance equation. Same thing, it's steady state, so I have no accumulation or depletion of exergy in the control volume. We have, it could come in with the, I'm sorry, not exergy. Next, do an entropy balance, okay? Did I finally get that right? First law, second law. Entropy, all right. So no accumulation or depletion of entropy in the control volume. We have Q dot CV coming in at TB, which is T naught. So that's the entropy transfer with the heat transfer coming in. No entropy transfer with the power, shaft power coming out, so that's 0. We'll have a M dot S coming in minus S naught going out, plus sigma dot CV. I stop, I pause. Did I get the entropy balance, the second law, correct? Look good? So we just take this equation and multiply by T naught. Put T naught there. T naught, they cancel. So now we substitute for Q dot CV to eliminate the heat transfer. If we eliminate the heat transfer, and I know I'm going to do a little bit of algebra here, I'm going to rewrite the energy balance equation eliminating Q dot CV using entropy balance. You get W dot CV is equal to M dot H minus H naught. So I kind of move that term right here, right there with the H minus H naught, plus, whoops, I'm going to do this, minus T naught S minus S naught. So I'm handling these terms right here, plus, that's a bad looking naught, isn't it? There's a naught right there, plus the KE plus the PE, those terms right there. I just handle those terms. That's all multiplying the M dot. Then we have minus T naught sigma dot CV. I know there's a lot of algebra, but I think you can get the algebra rearranged. First law, second law. With the second law, use it to eliminate Q dot in the first law. And there you go. Now we just have to understand this equation. You want to produce as much work per unit mass flowing through the system. What's going to decrease the amount of work produced? The presence of irreversibilities. If the system has no irreversibilities, sigma dot 0, it can't go negative, and you get the maximum, W dot CV divided by M dot, maximum, which is now just H minus H naught minus T naught S minus S naught plus KE plus PE. And you look at it and you say, it looks like a property, a new property to me. We'll call it, give it a name. We'll call it Exergy. We'll call it the flow Exergy. And voila, there you go. There's your quick derivation of the flow Exergy. Okay. Any questions? Yes, sir. Okay. Because I probably need to do this in a couple of steps. Take that equation and write it like this. Q dot CV is equal to minus M dot T naught, S minus S naught, minus T naught sigma dot CV. All right? Thank you. That's right. When 0 equal to 0, then W dot CV is maximum. Ready to solve a problem? Steam at 3 kilograms per second, 80 bar and 440 degrees C enters the turbine. So this is the temperature of the steam entering, the pressure, and that's the mass flow rate of the steam entering the turbine. Determine the flow exergy. So you want to calculate the property, E sub F. What was the definition of it? H minus H naught minus T naught S minus S naught plus KE plus PE. All right. At this temperature and pressure, can I get H? Can I find H for steam, H2O, at 80 bar at 440 degrees C? I sure hope you can. And as well as S. So can you find S at 80 bar, 440 degrees C? What about H naught and S naught? That's steam at the dead state temperature of 25 degrees C and the dead state pressure of 1 bar, right? Can you find the property H naught and S naught? Okay, good. Then the T naught you put in, you don't put in 25, you put in 298 Kelvin, true? Absolute temperature for the dead state. About this kinetic and potential energy. There's no information except for it says ignore the effects of motion and gravity. So we'll assume those are 0. And you can crunch and you get that the flow exergy is equal to 1380. The last one, or part B, what is the flow rate of exergy into the turbine? It's in units of kilowatts, but what symbol do I want for it? Flow rate of exergy into the turbine. Is that the mass flow rate times E sub F? It sure is. That's all it is. Is there a simple one, like maybe E dot M? Well, you could make that up, but I don't think the book uses anything like that. The book uses E dot Q and E dot W for the flow rate of exergy with heat transfer, the flow rate of exergy with work. But as far as I know, the book, but a different author of the book may use E dot M for the flow rate of exergy with the mass. Or you just leave it like this, M dot E sub F. You make that multiplication, you find it's 3924 kilowatts. Second law efficiency for turbine. So you have a turbine. Q dot's equal to 0. What's that mean for the turbine? It's well insulated, right? Well insulated turbine, no heat transfer. You have W dot coming out of that turbine. You have some inlet flow and outlet flow. Inlet 1 at mass flow rate and the flow exergy at 1. You could also put in H1, S1, V1, whatever property you wanted. Conceptually it's available, but for the second law efficiency or the exergetic efficiency of that turbine, we're really interested in E sub F, the flow exergy coming in, as well as the flow exergy going out. The turbine has only one M dot, true? You think this is steady state? Sure, it's steady state. Turbine operating under steady state conditions. Okay, no accumulation or depletion of mass in the control volume. Okay, now what we were interested in is a review. We had isentropic efficiency before, did we not? What was that whole efficiency of a turbine before? It was some where we're going to say the efficiency of the turbine, isentropic efficiency of the turbine is the power out divided by the power out, but this will be the actual power out, and this will be the maximum, assuming it's isentropic expansion through the turbine. Maybe this is W dot over W dot S. Okay, but without a subscript that's implying actual, and S means constant entropy. Constant entropy is isentropic expansion through the turbine. Okay. Well, you can divide this by M dot, you can divide that by M dot. Didn't change the definition of the isentropic efficiency. And then when you do an energy balance around that turbine, we find from the first law that W dot's equal to M dot times H1 minus H2. The enthalpy in minus the enthalpy exit. What happened to the kinetic energy in, the kinetic energy exit? Typically they're negligible in the energy contribution, so we just assume that kinetic energy change is negligible and the potential energy change is negligible. Okay? It's just the enthalpy change across that turbine. So for a review, the isentropic efficiency of the turbine is H1 minus H2 divided by H1 minus H2S. H2S. 2S. Is there a state 2S? It's this. You could put it on a different property diagrams. How about a temperature entropy diagram? Maybe put a dome, put a line at constant pressure. That's a bad looking line of constant pressure. Try that again. Line of constant pressure, a line of constant pressure. Okay? This is pressure high, this is pressure low. Maybe you're coming in with steam, it's slightly superheated. If you come straight down from state 1, you'll find state 2S. If there are irreversibilities, it's going to have an increase, and state 2 will be over here. So this is a review of our isentropic efficiency for the turbine, but now we want a new efficiency. It's called the exergetic efficiency. We already talked about the flow of exergy coming in. Wasn't that the mass flow rate, EF1? Wasn't that the so many kilowatts of exergy flowing in with the fluid? Guess what M dot EF2 is going out? It's a flow rate of exergy with the fluid. This flow in is going to be greater than the exit. Where did that exergy go? 2 places. In the shaft power or Destroyed. Destroyed due to irreversibilities. So if you write an exergy balance, it makes it a little clearer, but let's say it's steady state, and so what do we have coming in? M dot EF1 coming in, minus M dot EF2 going out, minus W dot CV, sometimes put a CV on that, minus E dot D. So this is M dot EF1 minus M dot EF2. That's that symbol I made up of E dot M. What came out of the mass flow stream? The flow stream went like this through the turbine. This is the rate at which exergy is coming out of the fluid flowing through the turbine. So difference between in and out. Make sense? That's equal to W dot CV plus E dot D. It either went to turning that shaft, what we want, or being destroyed through irreversibilities, what we don't want. So this then gives us a good definition. I think the book changes the symbol epsilon. Maybe we'll put a T on it. So epsilon for a second law efficiency or exergetic efficiency. It's what we desire. What do you desire? A lot of power coming out that shaft. Over what it cost. What did you have to pay for? Where did it come from? It came out of the flowing fluid, M dot F, which is M dot E sub F1 minus E sub F2. It came out of that flowing fluid. Did all of it come out of the flowing fluid and go into the shaft? No, some of it was destroyed due to irreversibilities. What could the highest or the greatest second law efficiency be for a turbine? Could it go over 100%? No, it's not going to go over 100%. But it could come up to 100%. Make sense?
What are typical numbers?
They're very close numerically to the isentropic efficiency, but they won't be spot on. So maybe it'll be 92%, 85%, 75%, somewhere. Okay. A well-insulated steam turbine operates at steady state with one inlet and two outlets. Oh, we're throwing you a curveball. One inlet, two outlets. See that? The properties are given in the table. Here's the table right here. Let's see. We got state 1 listed, state 2 listed, state 3 listed. Let's find them on the diagram. 1 is the inlet, 2 is an exit, 3 is an exit. See that? They have the M dot. Oh, for state 1, 15 kilograms per second is flowing in. How about the M dot for state 2? 3 going out and 12 going. Does that make sense, or do they have a problem with this problem statement? 15 in, 15 out. 3 and 12 is 15, right? All right. What about the pressure in? Wow, it's 4,000 kilopascal. That's how many megapascal? 4. How many bar? 40. You are good. You've got to practice these pressure conversions. They'll eat your lunch if you don't get them down, right? So jump back and forth between kilopascal, megapascal, bar. The book and the appendices really helps you with reminders of those unit conversions, but you could still ball it up. So it comes in high pressure, goes out, still pretty good pressure, 5 bar. Or 500 kilopascal, or half a megapascal. That's out at state 2, out the stream at state 2. But at 10, what about at 3, state 3? It's coming out at 10 kilopascal. Tell me a little bit about 10 kilopascal. High pressure, low pressure? Very low pressure. You would even call that a vacuum. Somebody a little mischievous, it's got a pipe right there, right? Steam's coming out of the pipe. They take a drill and they drill a hole in the pipe. Then they remove the drill bit. There's now a punctured hole in the pipe. Is air going to rush into the pipe, or the steam going to gush out of the pipe? In or out? The steam is going to, the air is going to come in. It's 100 kPa out here. It's 10 kPa in the pipe. Out here it's air in the room, like we're breathing. In the pipe it's 10 kPa steam. Holy, you have a vacuum? Where's the vacuum pump? Oh no, this is all made up. Or do we believe this? Do real power plants run with steam in pipes that are less than atmospheric pressure? Yes, and that is a mind-bending thought. All right? Try to wrap your head around that one. We'll try to beat that into you, but I try to beat it into students in Thermo 1, but we'll try it a little bit in Thermo 2 as well. But yes, it's a state of vacuum in that pipe. It's pure steam. They want pure water. They don't want air in there, mixed in there. They work hard to get the air that may leak in there or began in there to get out of there. Engineers do. Okay? But you want pure steam in the pipe, and yes, it can be at that pressure. Now notice they give you a temperature at state 3. Guess what that temperature, when they give you a temperature to 4 significant digits like that, just look at it. What's it cry out to you? Yeah. Hello, I'm the what temperature? I'm the saturation temperature at that pressure. It's two-phase. I forgot the quality. I probably have it written somewhere here. But the quality is, sorry, I can find it. The quality is 85%. X is 85%. So it's high quality steam coming out at state 3. Take a look at the temperature. Do you want to touch 400 degrees C steam? No, you don't. How about 240 degrees C? No, keep it far away from me. Right? So this is very high, dangerous things. Okay. These values of enthalpy and entropy we're going to trust. They look reasonable. All right? Okay. Now that we understand the information given, we try to answer these questions. Part A, what is the power developed? How am I going to solve for the power developed? I'm going to pause and I want you to write down the equation to calculate part A. Then if you get that one, move to part B. What's the rate of exergy destruction? And then the part C, what's the exergetic efficiency for this turbine? All right, we do an energy balance, true? Energy balance for that control volume. And after you do a little bit of work, you find that the power out's equal to the mass flow rate in at 1, carrying with its enthalpy at 1. And taking out at 2, its enthalpy at 2, and out at 3, enthalpy at 3. You should do that a number of times for a number of different problems and work it out, okay? Only a few of you had that, but it should be coming more second nature to you. So that's how you calculate the answer for part A. You're given the mass flow rates and the enthalpies, and if you make the calculation, you'll find that W dot is 12,670 kilowatts. So it's 12.7 megawatts. Okay, that's a lot of power out of one steam turbine. Now the second part, part B, what is the rate of exergy destruction? You can do the exergy destruction using the approach of an exergy balance, or you can just say exergy destruction's T naught times sigma dot and do an entropy balance to get sigma dot. True? Either approach works. Either approach works. Probably coming out of Thermo 1, your sigma dot's probably a little more appealing to you because you can do a second law of balance pretty quick. Okay, is that equal to m dot 1 S1, whoops, m dot, let me do this, 2 S2 plus m dot 3 S3 minus m dot 1 S1. This is the outflow of exergy. It has to be higher than the inflow of entropy. Okay? Does that make sense? If you calculate the sigma dot, the generation, you'll get so many 4.458 kilowatts per Kelvin. That the right units? Sigma dot? kilowatts per Kelvin? Sure. Then we multiply by T naught. T naught, they didn't give it to any T naught was given, right? So what do you assume? 25 degrees C, 298 K. And then you can calculate using this equation the Exergy destruction rate to be 1328 kilowatts. Okay. What is the exergetic efficiency? What is the exergetic efficiency? I know we like to have just plug and chug, and something for an exergetic efficiency, it's the flow of exergy that went into the work. So E dot W out. That's what you want, out that shaft. But it came out of the fluid. It came out of the fluid that flows. But it's like you have two streams. One stream goes from 1 to 2 and the other from 1 to 3. See that? I should change color to show that a little clearer. From 1 to 2 and 1 to 3. So what you say is, this is W dot that came out the shaft. We already calculated that from part A. But what we have is what came out with the fluid is the mass flow rate in the going to through pipe 2. That's from 1 to 2 this way. See that? Times EF1 minus EF2 plus M dot 3 EF1 minus EF3. Okay, that'll work. But this calculating that is a hard thing to do. Let's go back and think about this. I have a Exergy balance equation. All right. I'm looking at trying to do this without using any more real estate on my screen. I'd hate to scroll down. But this power, okay, came out of what came out of the fluid stream. So this E dot that came out of the mass fluid streams either went into turning the shaft, producing the power, or was destroyed. True? Does that make sense? So why not use the Exergy balance equation to rewrite the denominator such that the exergetic efficiency of the turbine is the power out. Hey, that's what we just calculated from part A, right? And the power out divided by the plus the destruction. And so when you calculate the exergetic efficiency of the turbine, or the second law efficiency of this turbine, you find that it's right at 90.5%. Comments, questions? Chew on that for a while, okay? Solve a lot of problems. Thank you for your attention. I'll be in my office if you have any other questions.